Okay, question 9. A bit of an astronomy one, this one. First off, the sun reaches its highest point in the sky on Midsummer's Day. So just to remind you, when we get to summer, the Earth is tilting towards the sun, and therefore the sun will appear higher in the sky. You'll have noticed at winter time, when you look at the sun, it never gets all that high. That's because we're tilted away from the sun. So when we talk about the highest point in the sky on Midsummer's Day, that's kind of the very middle of the summer. We're tilted as far towards the sun as we possibly can, and therefore the sun appears as high in the sky as it's possible to get. You were asked to work out how you can use this to figure out the time taken for the Earth to orbit the sun once. The time taken for the Earth to go round the sun once is a year. Do be careful with that. Some of us got a bit confused and thought it was a day. That's the time for the Earth to rotate once. So we're looking at using this fact to figure out how long a year is. Once you know that, it's pretty straightforward. You're basically going to work out when Midsummer's Day is. That's when the sun is at its highest. You're then going to time it until it happens again, and that's a year. That's how it works. So mark scheme wise, they were looking for you to say start the clock when it reaches its highest point, Midsummer's Day. Stop the clock when it reaches its highest point again. That's our next Midsummer's Day. You could talk about how... That's really not helpful, phone. Go away. You could talk about how the shadow is going to be the shortest on Midsummer's Day as well. But seeing as they've mentioned that the sun is at its highest point, you didn't necessarily need to mention that. Second part, we're given the radius of the Earth's orbit and the time taken for one orbit, which, remember, one orbit of the sun, we're talking about a year, so 3.2 times 10 to the 7 seconds, that's a year. 1.5 times 10 to the 8 kilometres, that's the distance between us and the sun. So here's a nice little diagram. That's the best diagram of the sun that you'll ever see in your entire life. Nice round ball of plasma. Here's the Earth, and it goes around there. So the distance here, that whole distance there, 1.5 times 10 to the 11 metres. It's given as 1.5 times 10 to the 8 kilometres, and that's what you've got to be careful with, remember. Kilometres means 1,000 metres, so we're looking at 1.5 times 10 to the 11 metres. The famous number in astronomy. The time for one orbit is just a year in seconds. So you're given an equation to work out the orbital speed, which is v is 2 pi r over t. I mean, not that it matters, but hopefully that makes sense. 2 pi r is how far it's going to travel, and t is how long it took to go round once. Yeah, a year. So you're going to work it out. V is 2 pi r over t, which is 2 pi times r. That is poor planning, isn't it? We've run out of space. My orbit's too big. Two pi r over t, which is equal to 2 pi times 1.5 times 10 to the 11 metres divided by a time of 3.2 times 10 to the 7 seconds. And this is kind of cool, because what it will do is it will tell you how fast the Earth is going around the sun. And the answer to that is very. Put the numbers into the calculator, it will give you 2.9 times 10 to the 4. 2.9 times 10 to the 4 metres per second. And it's in metres per second there in the exam paper, so we'll leave it there in those units. 2.9 times 10 to the 4, so 29 kilometres per second. That is how fast you are travelling right this minute as you orbit the sun along with everyone else on Earth. Okay, the final part of this is part C. The sun is likely to remain as a main sequence star for 2,000 million years. Why is the sun not exploding now? It's a 6 marker, so we're going to need to go into a reasonable amount of detail here. So why isn't the sun exploding? Well, if you think back to your diagrams showing the life cycle of the sun, you'll recall that the sun isn't due for an explosion, not now, not ever. What will happen is it will turn into a red giant. The reason it doesn't go into a red supergiant and then explode is because it doesn't have enough mass. You need to have a star several times the mass of the sun in order for it to go through the whole explodey thing. So probably the easiest thing is if we just pick out what it says in the mark scheme and show you where it's coming from on that one, whilst I scrabble around off camera to find that mark scheme. There we go. I will seamlessly pad out the time with some top quality pattern. There we go, 9C, good stuff. So your best bet really when you're looking over your own answer is to see how it compares and the points that we were going to make. So just to draw your attention to the sort of things we're looking for usually, we're looking for your knowledge and understanding of the material in your answer, of course. You don't have to say everything in here, but it gives you the general explanation. You wouldn't need to say everything even to get 6 marks, but this is the general idea. And then we've got our kind of descriptors, so we'll come back to those in a minute. We'll just explain how we know that the sun isn't, well, why we know the reasons behind the sun not exploding at the moment. That was terribly explained. So let's take it through step by step. Gravity is an attractive force. You would get credit for saying that sort of thing. I know it's obvious. Gravity is kind of pulling all the stars in, which is your second point. So you've got your sun, in this case, your star, in this case the sun. It's being pulled in all the time by gravity. So all of the gas on the outside, all the plasma on the outside, is being pulled in by the force of gravity. Okay, on the inside you've got fusion happening, so in the centre of your star, in this case the sun, you've got nuclear fusion happening. It releases a lot of energy, a lot of thermal energy, and that gives rise to, as you can see here, an expansion force. So we've got gravity pulling the sun in on itself, but you've also got this energy from fusion sort of being given off, and that gives rise to an expansion force. Sometimes it's described as radiation pressure. So you've got all of this energy trying to get out, you've got gravity pulling it in. At the moment those two forces are nicely balanced. So it says the sun is currently stable because these two forces are in equilibrium, they're the same size, and that's why the sun remains the size that it is today. And it will continue to be like that until eventually it isn't like that anymore, and that has to do with the point where it kind of finishes. Sometimes people describe it as burning through its fuel. Of course, we're not burning anything, we're going through nuclear fusion, but when you run out of elements to go through with nuclear fusion with, that's when the star starts to change. The mass of the sun is an important factor, as we've said. If you don't have a large enough star, it won't go through supernova. So the red supergiant type star is the one that goes into the supernova, the explosion. Our sun can't do that. You need to have, 3 or 4 times the mass of our star, the sun, in order to get that supernova stage out of it. So what will actually happen to our sun, not that you needed to say in the question, is it will go to a red giant and then eventually go down to the white dwarf kind of route, and then eventually it will cool down to become a black dwarf, but the universe isn't old enough at the moment for those stars to exist. Good. So if you're going for, well, we're all going of course for the high end of this, so for 5 or 6 marks you need to demonstrate accurate and relevant physics understanding throughout, understanding of the scientific ideas detailed and fully developed. So a clear, good answer with lots of useful scientific ideas. An explanation that is well-developed structure which is clear, coherent and logical. So that's kind of a descriptor there for your 5 to 6 mark questions that will apply regardless of what the actual question is asking for. It needs to be clear, it needs to be logical, it needs to sort of hang together properly, which is what the coherent thing means. Kind of the ideas follow on from each other, just like we've got here. As you follow that argument, you can see why it is that the sun isn't going mental. Good, that is question number 9 done.